All right, QQT time. So this one really reminds me of the one I did last week for Physics C. This one's just slightly easier. So we got a hinge supporting a beam, and then there's a cable that's balancing it as well. And I imagine we're going to be asked about all the different ways that this balances. Okay. So the following rectangle represents the beam in figure 1. On the rectangle, draw and label the forces, not components, exerted on the beam. Okay. Well, uh, we have a beam. We got the word uniform. So since the beam is uniform, that means that right in the middle of the beam, we can give ourselves a gravitational force, mg. And then also on the end of the beam, we have a tension force, and that's going to be roughly the same angle as the tension drawn in the figure. I don't think they really are going to care that much. And then don't forget about the hinge force. When I did Physics C, I initially even forgot it. But again, this is not balanced right now. There is definitely a net force to the left on this beam right now. So there has to be a supporting normal force caused by this hinge right here. Again, we really don't know too much about it, but I definitely know that it's going to be directed to the right in some way. And this is normal force, hinge force, pivot force, axial force, something like that. But you need all three of these. So you need a straight down mg at the middle of the beam, you need a hinge force at one end, and a tension at the other. And you know what? I'm going to make it at least try to balance component wise of my tension force. Although that doesn't really matter. I'm surprised they didn't mark the center of the beam on this at least. Now, instead of the string being attached here, it's attached lower. So theta 1 was this, and theta 2 is dropped down a bit. There was a question just like this on Physics C this year. So if we lower the angle, what happens to the required tension force? So, again, I think the best way of doing this to get the answer before we even justify it is to think about extreme cases. So, extreme case analysis is super useful for us as physicists. So, let's see what happens if theta equals 0. Well, if theta equals 0 and the tension force is like this, well, that's not exerting any torque. So that would mean that the tension force has to be like infinity, which this doesn't make sense. So clearly decreasing the angle all the way is going to make your tension force required go up. And why does that make sense? Well, it's because it's not all of the tension that's exerting the torque on the beam, it's the vertical part of tension. So if your tension is horizontal, you don't get that much of your tension force actually helping you to balance the torque of the mg. So, couple ways of doing this, but this means that tension 2 is definitely greater than tension 1. So, briefly justify your answer using qualitative reasonings beyond referencing equations. So, since I'll abbreviate a bit just so we're not here forever. You write this out. So the the torque in case 1 has to equal the torque in case 2, because we're not balancing anything different. It's still the mg and the load that needs to be balanced. So since theta decreases, that means sine theta decreases, which means that the torque from tension decreases. This means more force is required to generate the same torque. This should be valid. I know it says beyond referencing equations, but we did more than reference equations. We said that since theta is decreasing, sine theta is decreasing, which means that the torque decreases. If you wanted to say this in more words, I just didn't feel like writing them, you would say that as theta decreases, the torque generated by tension decreases because less of the cable is perpendicular to the rod. So this means more force is required to generate the same torque. And now we got to derive it. So this actually is not as bad as it looks. So we know that the net torque has to be equal to 0 on this rod about any pivot point. And due to the fact that we know nothing about what's going on at this hinge, we pick this to be our pivot point so we can kill the hinge force. So this means we only have two forces to consider that are generating torques. We have the mg force, and then we have the tension force. I meant to change color. And then we have the tension force. So this tells us that the tension caused by mg, the torque caused by mg has to be the same as the torque caused by the tension force. And mg is already perpendicular, so there's nothing we have to mess with there. So the torque is just mg times the distance at which it acts, which is L over 2. That's not a loud variable, but it's going to cancel. And then the tension force, you could do a couple things here. You could do R cross F. You could do lever arm. When we have these cables like this, I like to think about this question as what's causing the torque. So Ft is not fully causing the torque. The thing that's causing the torque is the perpendicular component of tension. And that is just going to be Ft times sine theta. So what's important is that you'll pick up a sine theta here. So again, if this angle's theta, that means that this angle is also theta. So the across red component is Ft sine theta. So we have a force of Ft sine theta causing our torque at a distance of L away. Again, not the only way of doing that, but that cancels. So we get Ft equals mg divided by 2 sine theta. And there's our answer. Is your derived equation in part C consistent with your justification in part B? Explain your reasoning. So, again, we found that Ft is equal to mg divided by 2 sine theta. So again, this is what makes it a QQT. We did it qualitatively and said, without even doing the math, the tension should increase when theta decreases because physics reasons. We said less of tension is perpendicular, so you get less torque, less bang for your buck, so you got to do more force. Here, we are allowed to just say, I don't know the physics, but the math says this. So we're allowed to just say Ft is proportional to, let's see, what's changing. So this changed theta from a big theta to a small theta. So F is proportional to 1 over sine theta. So if theta decreases, 1 over sine theta increases, which means Ft increases. So this is consistent. That's all you have to say. other things like sine theta is in the denominator. So if you decrease the denominator, the whole thing increases. Thus, theta tension when tension at theta 2 is greater. And then if the string is cut, the beam begins to rotate about the hinge with negligible friction. On the following axis, sketch the angular speed of the beam. They really like this question. They've been asking this one for a while. A couple years in a row. Physics C has been asked this a lot. So this is the zero case. And then the beam is going to rotate. And it's going to become vertical. So we're going to start at rest, and we're going to allow it to rotate about the hinge here. So again, when you're dealing with graphs, you usually get a point just for identifying the start and stop. So if I'm starting at rest and I'm ending vertical, well, this thing's definitely swinging as it's going vertical. So it's definitely going to end with angular speed. So it starts without angular speed and it ends with angular speed. And now we got to think what connects them. And typically in physics, it's either concave up, concave down, or straight line. So let's see which one. Well, slope is going to be equal to angular acceleration, which is proportional to the torque. So we're just going to see how the torque evolves on this thing as it swings. Well, notice that at the start, the torque is maximized because all of mg is perpendicular to the rod, because that's what happens when you cut the string. It's just mg causing the torque. And then as the rod swings, mg becomes less and less and less and less perpendicular to the rod until you get to T final, where it's not doing any torque. So this means our slope decreases. So it's speeding up the most at the start, and then it eventually flattens out. So we get this nice concave down curve. Let's see, one more. I'll give myself one more chance to draw this nicely. So just say that this is concave down. And we don't even have to justify the shape. We just have to say that it's concave down. So again, notice my slope is really high at the start, and then it flattens out. All right, now on to point breakdown. Okay, 12 points again. Let's see. Okay. Sticking with it, I wouldn't be surprised if you just get a point per force here. Because it's really common to forget this. I mean, I even forget it if it's not labeled sometimes. You have to put them in the right spots too. So you get a point for the hinge force at the left, a tension force at the right, and an mg down the middle. Direction isn't super important, but I do think you have to point the hinge force to the right at least. That's the only guarantee. Then, just given the space here, I bet point B is, it's probably just 2 points. A point for the selection and a point for some variation of the torque required is less. Or sorry, the torque generated is less, meaning the force is more. But this could easily be a 2-point justification, so this could be 3 points, I'm not sure. Then if we go over here, this seems like 3 points to me. You probably get a point for identifying that the two torques have to be equal. You probably get a point for using the correct distances, and then you get an answer point. Is your derived equation consistent? Get a point for the answer, get a point for the justification. And then lastly here for the graph, probably 2 points again. 1 point for starting and stopping in the correct spot. So a graph that goes up gets you 1 point, and a graph that's connected with a concave down curve gets you the other. And if we sum that up, we get 4, 9, 12. Perfect.